All right, now let's see how to actually estimate the value of our derivative graphically. So in this little example, we're given the graph of x squared, and we're going to use this graph to estimate the value of the derivative of this function at x equals 1. All right, so what are we going to do? Well, we're going to sketch the tangent line at point P, and we're going to try our best. This is going to be an estimate after all. It's going to be an approximation, so try your best. And then once we have our tangent line, we're actually going to determine the slope of the line that we drew. All right, so how do we start? Well, we're going to draw our tangent line at point P. Where is point P? Well, we actually get that information right from this value that we're trying to estimate. We want f prime of 1. This tells us x is equal to 1. So we're interested in what's happening at x equals 1. So that's where we draw point P. So we go x equals 1 on our x-axis, read up until we see the corresponding point on the curve. So point P has coordinates 1, 1. And we could also get the y-coordinate by just plugging in directly into our original function x squared here. So we can see from the graph, it looks like point P has coordinates 1, 1. But we could also get the y-coordinate by plugging in our x-coordinate. All right, so we know where we're going to be drawing the tangent line. Now let's actually draw it. And, well, let's see how this goes. All right, so we want when we draw this, we want our tangent line to just touch the curve, so that when we zoom in at that point, it looks like our tangent line and our curve are kind of pointing in the same direction. So let's try our best. See how this goes. All right, that's not too bad. If we zoom in on that, yeah, that's not too bad. I think I kind of captured what our function's doing there at that point. Okay, so that's a fine tangent line. So try your best. All right, so now we have our tangent line. Now we actually want to estimate the slope of the tangent line at this point. And so why do we do that? Why are we trying to estimate the slope of our tangent line? Well, we know that for functions like this, we can think of the derivative f prime, in this case 1, f prime of 1, as being the slope of our tangent line at x equals 1 at point P. So f prime of 1, we're really thinking of it as the slope of our tangent line at x equals 1. That's one interpretation. So how do we calculate the slope of a line? Well, we have our line drawn here. So the slope is just the change in y over the change in x. So how do we determine the change in y over the change in x? So what we can do is we have our tangent line drawn. We know point P is on this tangent line. So to find the slope, pick some other point and then just calculate. So look at how much y changes going from one point to the other and see how much x changes going from one point to the other. And when you pick this second point, try to make it a point that's kind of easy to determine the coordinates for. So if I'm looking here, I have all these points on this line to choose. Pick an easy one. And it looks like this one is pretty good. Looks like it goes through the grid lines, or pretty close. So this point to me looks like it might be 2, 3. And our point P, we know this one, and that had coordinates 1, 1. So now I have 2 points here that I can pretty easily determine the values for, the coordinates for. And again, these are just approximations. So it might not be exactly 3, might not be exactly 2, but we're approximating. We're trying our best. All right, so we've picked this second point. We made it easy. Now we just want to determine, the change in y versus the change in x. So the way to determine this is just kind of move up. Try to move to that line or move to that second point. And when we do that, we see that we move 1 unit to the right, and then we move 2 units up. So we plus 2 units up, and then plus 1 unit to the right. So when we move to the right, that's a positive change in the x direction, and we've moved 1 unit, so it's a positive change in the x direction. And then when we move 2 units up, that's a positive change in the y direction. So we're going up 2 units. So our slope then is change in y over change in x. It's 2 over 1. Change in y, we went 2 units up, going from one point to the other. And then our change in x was 1. We went over to the right 1 unit, going from one point to the other. So our slope here is 2. All right, so that's the idea. Is given the graph, find your point of tangency, draw in what you think the tangent line would look like, pick a second point on that line, something that's easy to determine the coordinates for, and then you can either kind of graphically do this sort of thing where you see, okay, I went to the right 1 unit and then I went up 2 units. Another way to do that is just with our slope formula, though. So you could do the for just the general slope of a line. How do you find the slope of a line connecting 2 points? Well, it's just the difference of the y coordinates and then the difference of the x coordinates. So if we wanted to, once we've identified the coordinates, we could have just done change in y was 3 minus 1, change in x was 2 minus 1, and we end up with the same value, 2. So you can kind of either just kind of visually do it using the grid lines, or use the regular slope formula for the slope of a line connecting 2 points once you've identified that second point. All right. Let's think about, we have this whole graph. And it sure would be nice if there was a formula that allowed us to determine the slope of our tangent line at any of these places. Any of these points on our graph. It would be really nice if there was just a formula that we could plug into that told us what the slope was at any of these points. And so, well, there is. It's the derivative. So if we have, in this case, our curve, which is y equals x squared, and we've seen how to actually calculate the derivative using the limit definition, and I don't know if we've done x squared by itself, but you could do it using the limit definition. You'd get 2x. And so the way to interpret this derivative is it gives us the slope of the tangent line at any point, any x value along this curve. So it gives us the slope of the curve, or the slope of the tangent line, at any x value. So what did we do? Well, in the last, over here, we graphically estimated the value of our derivative by drawing in the tangent line. But if we had this formula of the derivative y prime equal to 2x, what we could have done instead is that at x equals 1, what is the slope of our tangent line? Well, the slope is equal to 2 times 1. We would just plug 1 into this derivative, and we get 2. And so we could repeat this experiment here at any x value, at any point along this curve, and figure out what the slope is. So we found the slope at the point where x is equal to 1. The slope is 2 there. But we could play this game, you know, all day long. We could sit here and just pick different points and determine the slope at that point. So, you know, we could pick, you know, what's the slope? Here's at the slope at x equals 1. We found it was 2. What's the slope at x equals 2 at this point here? So if we were interested in that, we could go to our nice derivative formula and just plug in to figure out. So at x equals 2, the slope would be 2 times the x value. 2 times 2, which is 4. So if we were to draw in the tangent line at this point, the tangent line that we're drawing in should have a slope of 4. So we could just do this all day long. So let's do it. No, let's do one more point. Let's do -2. This point over here. What would be the slope at x equals -2? Well, we could draw in the tangent line and then estimate what the slope is. But we know we have this nice formula here, this nice derivative formula. So what we're going to do is we're going to take that derivative formula. We're going to take the x value that we're interested in, and we're just going to plug it in. So -2, plug it into our derivative formula. And we get 2 times -2, 2 times x, which is -4. So the slope over here is -4. And you can kind of see that that makes sense. Down here, it looks like our curve, if we were to draw in our tangent line, it's not too bad. If we were to draw in our tangent line over here, it looks like it's pointing down. So the slope is negative. And then on the right side of this graph, we see if we already did draw in the tangent line at x equals 1 here, and we saw that it was pointing up. So over here, the slope would be positive. And that's because our tangent lines are all pointing up on that side. All right, so, you know, this is really just meant to show or give us some appreciation for how special this formula is. This having this slope formula here of 2x allows us to figure out the slope of our tangent line at any point just by plugging in. So, you know, we saw how to kind of graphically estimate that. But sometimes, when we're lucky, we have this nice slope formula, our derivative, nice formula for our derivative that we can just plug into and calculate it directly.